Welcome to Feza Gürsey Center's and Harish Chandra Research Institute and IPM Number Theory Seminar Series. Our speaker is Erman Işık from the University of Ottawa, and he will talk on the growth of Tate-Shafarevich groups of p-supersingular elliptic curves over anticyclotomic ZP extensions at inert primes. And Erman was one of our former graduates from Boğaziçi University. So please, Erman.
Thank you very much for the invitation and introduction. I'm so happy to be here. Thank you for having me. I'm going to talk about the growth of Tate-Shafarevich group. Well, the title is self-explanatory, actually. And here is the, oops, did I mute myself? No. Yeah, so here is the outline. I will start with talking about the Iwasawa's growth theorem. Then I will introduce Tate-Shafarevich groups and Selmer groups of elliptic curves. Then I will talk about the cases where regarding the growth of Tate-Shafarevich group for ordinary and supersingular primes, but over the cyclotomic extension. Then I will state our main theorem, and I will conclude with explaining the idea behind the proof. So let's K be a number field and CLK be the class group. So we know it is finite. And the question we are asking is, if we have a tower of number fields, can we predict the behavior of the class group, at least asymptotically? Well, when we ask these questions for the general towers, the answer is not easy to handle. And but if we restrict ourselves to certain towers, and if we focus ourselves to p-silo subgroups of those class groups, then we get a nice formula. So they behave astonishingly good over these classes. In general, Iwasawa theory concerns the growth of arithmetic objects over certain towers. And if I need to speak precisely, as I said, we are talking about p parts of class groups, but when we talk about the arithmetic objects, we are talking about actually the Selmer groups. And the tower I'm talking about is actually a ZP extension, which is a extension of K, my number field, whose Galois group is isomorphic to the additive group of periodic integers. And if we have such an extension, we can regard it as a sequence of fields where each individual layer, at every layer, the Galois group is isomorphic to Z mod P to the NZ. So the question is, do we have ZP extensions all the time? Well, let's focus on the unique subfield Qn of Q adjoint with Z P to the N. And this unique subfield is chosen as the Galois group is Z mod P to the N. And we take the compositum. It turns out that we have a ZP extension for Q, which is called the cyclotomic ZP extension. In general, if we have a number field, we can obtain a cyclotomic extension for those number fields. And the question is now, do we have more? And if we denote R1 by denote the number of real places by R1 and the number of complex places by R2, Leopold conjecture predicts that the number of independent ZP extensions of K is actually R2 plus 1. So we have that many of independent ZP extensions. And Brommer proved that Leopold conjecture holds true if we are focusing on the abelian extensions of Q. So indeed, if we have a number field, we have more than one independent ZP extension. So let me go back to the original question I asked. So let's say AN denotes the p-silo subgroup of the class group. So we have whose size is p to the en. And Iwasawa in 1950s proved that we can find some constants, which I will mention how to obtain that, where they come from, such that asymptotically we have this formula where e to the n is equal to nu times p to the n plus lambda times n plus v. And Iwasawa predicted that if we are focusing on the cyclotomic extension, this new part vanishes, so we have even better behavior. And if we are talking about abelian extensions and cyclotomic ZP extensions of those abelian extensions, this is the case, proven by Ferreira and Washington. And how do we obtain such a result? Well, the key ingredients are the following. So by class field theory, we can see this p-silo subgroup as a Galois group of an extension of this nth layer. Ln denotes here p Hilbert class field. So, and we collect all those things together. So this idea here, collecting all finite pieces together, obtaining an infinite object, is the main approach of Iwasawa theory, which I will mention later. And if we take the compositum, the inverse limit, and define the Galois group, the picture will look like that. So we have our base field. Here is the ZP extension. And we interpreted this Galois groups in terms of p-silo subgroup. And we define this inverse limit. And now what we need to do is to first obtain some information about this and be able to carry this information to the finite layer. So we need to be able to have some kind of a elevator that takes me from infinite tower to finite layers. And this ingredient is called the control theorem. Basically, it sees this objects as some kind of quotients of this infinite object. So basically, this control theorem says that the behavior at every layer can be controlled by this infinite object, which turns to be a Iwasawa module, which I'm going to define later. And the other thing, actually, let me define. So as I mentioned, we are able to define the action of this ZP extension over that, and that brings us to the following definition. And this is the idea in the Iwasawa theory. We define Iwasawa modules over this Iwasawa algebra, which is defined as the inverse limit of this group rings. And it turns out that we can find this Iwasawa algebra is canonically isomorphic to the ring of power series invariable Xn over ZP. So as I said, the structure of A infinity over lambda is key. It allows us, so we have a structure theorem for such modules, and this structure theorem allows us to express these modules in terms of elementary lambda modules. What are they? So let's say we have a finitely generated lambda module. Then we have called pseudo-isomorphism, a homomorphism with finite kernel, a co-kernel. So this Iwasawa module is isomorphic to this elementary lambda module. So this right-hand side called elementary lambda modules, where we have these polynomials. Such polynomials are called distinguished polynomials. So as you can see, it has more or less a structure of a module over PID. We are almost there, but not. But we can ignore this finite kernel, a co-kernel part, because this bit actually carries the most important information regarding the Iwasawa module. So this is the idea. So by combining these two, So this bit gives us the information over A infinity, and using the control theorem, we can carry this information to finite layer and obtain the growth formula. But as I mentioned, this structure theorem allows us to define Iwasawa invariance. So basically, you define nu as these numbers, and lambda as degree of this distinguished polynomials to the whatever degree they have in the structure theorem. Moreover, you can also attach another important object, which is called the characteristic ideal. So if we restrict ourselves to the torsion lambda modules, we can define the characteristic ideals as the annihilators of Iwasawa modules. So basically, we count how many times this n is divisible by p, and also this polynomials. So as I said, using these two important tools, before going back to the Iwasawa's growth theorem, I want to mention one important thing. So this characteristic ideal also pushes us to study further regarding these objects. So they allow us to study something called p-adic functions, and also the Galois representation, hence the Iwasawa main conjecture. So let me introduce how it looks like. So if you have arithmetically interesting objects such as elliptic curve, abelian varieties, modular forms, so on, you can attach them a Galois representation. And the moment you are able to attach a Galois representation, you can go two ways. Either you can go analytic direction and you can define a L function, which is a complex function. Also, you can go cohomological direction and you can define Iwasawa theoretic Selma groups. And these Selma groups are Iwasawa modules. Therefore, you can define characteristic ideal over them. And also, like this is conjectural, but every time you have a L function, one expects to have p-adic counterpart, a p-adic L function that interpolates the values interpolates certain values of L function. And Iwasawa main conjecture tells that this characteristic ideal is generated by the p-adic L function, which builds a bridge between analytic world and algebraic world. So I will mention this bit and how it is important later. So let me go back and this lambda and nu appears here because we define this Iwasawa module and so on. So if we have those tools, can we extend these tools to study other arithmetic objects? So in our case, obviously, I will be focusing on elliptic curves. So let K be a number field and A be an elliptic curve defined over K. And by Mordell-Weil theorem, we know that the rational points have a structure where we have this finite bit. Also, we have this called algebraic rank. And there's also an important theorem, $1 million worth, predicting the relation between this algebraic object and analytic object, which is the order of vanishing of the associated L function at 1. So the question is, okay, studying this is worth $1 million problem, but let's not trying to get the structure of that. Let's say if we focus on this ZP extension, can we get asymptotic behavior? So generally, this kind of things are way easier than dealing with the individual objects. And what are the objects that allows us to study this rank, basically? So the first one is actually called Tate-Shafarevich group, and it is defined as follows. So we have this, again, number field and integer defined over this one. And for any finite extension, the Tate-Shafarevich group is the kernel of the localization map between these cohomologies. And what we know about them is the Tate-Shafarevich group is torsion abelian group. Also, the Pontryagin dual of the primary part is a finite generic ZP module. So we are heading towards what we want. Also, conjectural it is finite, and it is an important tool to study the rational points of elliptic curves. Precisely, the size of it plays a crucial role in the studying of Mordell-Weil rank. Also, there is another version of BSD conjecture that formulates the leading term in terms of certain objects, and the Tate-Shafarevich group also appears in this formula. So another important object to study the Mordell-Weil rank is called Selmer groups, and we obtain them as follows. So we have this exact sequence which allows us to define long exact sequence, and we can extract the following short exact sequence. Basically, we are able to embed the rational points into this cohomology group through the Kommer map. And we can play the same game for the localizations of this field at every place. That gives us a certain diagram. Maybe I should have put it there, but regardless, this diagram, this one, and the localized version of them allows us to define the Selmer groups, where we take the collection of objects in this whose restriction lies in the image of the Kummer map. So this kappa V is the Kummer map for every local field. So how do they allow us to study the Mordell-Weil rank? Well, as I said, it contains the rational points, and the quotient is actually Tate-Shafarevich group. So following the idea of Iwasawa theory, we go to the infinity part and define P infinity Selmer group by taking the direct limit of these Selmer groups. And it turns out that the picture we get looks like this. So this bit is isomorphic to QP divided by ZP to the Mordell-Weil rank of this elliptic curve over it. So this bit carries the information regarding the Mordell-Weil rank, and we are able to embed it into this P infinity Selmer group. And also the co-kernel is the P part of the Tate-Shafarevich group. So if this happens to be finite, which is conjecturally true, what we obtain is the Mordell-Weil rank of A or L is actually ZP rank of the Pontryagin dual, which is this object here, of this Selmer group. So if one thinks about the Iwasawa main conjecture, if we have something like that, this the characteristic ideal of this is generated by the critical function, which is related to the L series. So this relation, Iwasawa main conjecture, and the fact that the rank of this object is related to Mordell-Weil group allows people study the Burchard-Simon-Narton-Dyer conjecture in certain cases. So they are indeed important tools to study the Mordell-Weil ranks and answer some questions, basically. Okay, so I will be mentioning now the known cases regarding the behavior of the Tate-Shafarevich group over the cyclotomic ZP extension of Q. So let's say we have an elliptic curve defined over Q, and let's fix an odd prime of good reduction. So Mazur started the study of P-Selmer groups in order to obtain results regarding the Mordell-Weil group. So let me remind you, that was the cyclotomic ZP extension, and we had the finite layers. And we also assume that the p primary part of this Tate-Shafarevich groups are finite, and this is the sizes denoted by this. It turns out that if one wants to study behavior of this ENs, the results depend on whether you have an ordinary reduction or supersingular reduction at this prime. So let me show you what happens in the ordinary case. And when we move to the supersingular case, I will explain why we have this difference. So if E has ordinary reduction at P, then we know due to Kato that the Pontryagin dual of this P infinite Selmer group over this ZP extension is torsion, which means we have Iwasawa invariance. Also, Kato and Rorley proved that the rank of elliptic curve over the ZP extension is finite. Also, Mazur proved the control theorem. So we have also the elevator that allows us to move from infinite section to finite layers. And it turns out that all those information gives us the following formula. So the difference between the sizes can be written in terms of Iwasawa invariance and the rank of this elliptic curve over the ZP extension. What happens if we have supersingular reduction? So it turns out that this P infinity Selmer group is no longer cotorsion. So the Pontryagin dual is not torsion. So we need to obtain, but there are other several reasons that this part is more complicated, but I'm just focusing on the parts that is related to the topic of the talk. Kobayashi introduced two modified Selmer groups, which are called plus-minus Selmer group. When AP, which is given by this formula here, E bar denotes the reduction of my elliptic curve at P. When APA is 0. And also he proved that these modified Selmer groups are cotorsion. Hence we have Iwasawa invariance. Well, he actually proved more. As I said, I'm restricting myself to the topic of the talk. And what we can do with these guys is to think them as objects that control half of the layers. So this is what they are assigned for. And Kurihara, Kobayashi, and Pollack obtained asymptotic formula regarding the behavior of the Tate-Shafarevich group. So this time, as you can see, we have this number, and this Iwasawa invariance appear. Also, this R infinity is again the rank of E over ZP extension, and also due to Kato and Rorley, we know in this case it is finite. This Qn is an explicit sum of powers of P. And this Iwasawa invariance, the sign depends on the parity of M. So if it is plus, we have something. If it is minus, we have something else. So we get this sort of formula. So for a P not zero case, Sprung proved a similar formula using the flat-sharp Iwasawa theory. And later on, Ley, Löffler, Zarbe studied the growth of Kato-Shafarevich Tate groups for higher weight modular forms, obtained similar formula. And Ley and Lim tackled the question, again, over the cyclotomic extension, but for certain number fields. So I will go back to this case at the end of the talk again. So what happens if you go further? So generally what people do is to take imaginary quadratic field. It is the next candidate to study and focus on the anticyclotomic extension. Recall that the number of independent ZP extensions is R2 plus 1. In this case, we have two ZP extensions, and one is cyclotomic, the other anticyclotomic. And this extension is dihedral over Q. So this is actually the defining property of that. And we know it exists due to the Leopold conjecture. So let's say we have a auto prime of good reduction, which is unramified in this extension. If P splits in K and these two primes splits completely in the anticyclotomic extension, under certain hypothesis, Biovita and Pollack tried a similar formula regarding the behavior of the Tate-Shafarevich groups. If we further assume that P is greater than or equal, P is equal to 5 or greater than 5, and the Hegner hypothesis, Speriani proved that the Tate-Shafarevich group has trivial corank over the associated Iwasawa algebra. And here is the assumptions for our result. So we have an elliptic curve defined over Q. We fix an auto prime where E has a good super-singular reduction. And also we assume that AP is 0. Also, we fix an imaginary quadratic field such that P is inert. So this is the new case. Also, well, we assume P doesn't divide the class number and so on, but we assume that the plus minus Selmer groups that we are going to define in our case are both cotorsion. So we are working under this assumption, which I will mention later on. And we denote the nth layer by Kn. And this is what we proved. So the Mordell-Weil ranks of n over these finite layers is bounded independently of n. And if we assume the P part of the Tate-Shafarevich group is finite and define R infinity due to this result, and denote the Iwasawa invariance for the plus minus Selmer groups, we have the following formula. So for large enough n, the difference is equal to twice of some sum of P powers and Iwasawa invariance and the model are infinite, basically this number. So this is what we proved. And now I will mention the idea behind the proof. So this part might be a little bit messy, sorry for that, but I try to keep it as simple as possible. So our proof relies on a system of local points introduced by Burungala, Kobayashi, and Ota in 2021. These local points allowed us to construct plus-minus Coleman maps, hence allowed us to define plus-minus Selmer groups. And the plus-minus Selmer group look like that. They lie in this P infinity Selmer group. And also they control the half of the layers, like in the Kobayashi's case. But they are not defined in a way that Kobayashi defined with the trace compatibility relation. But they play the same role that they did in Kobayashi's case. And as I mentioned, we assume that these Selmer groups are cotorsion. And we follow the ideas of Kobayashi. Basically, what he did is to study the growth of certain projective systems, which are now called Kobayashi ranks. So if we have a projective system of finite GNZ-P modules with finite kernel and co-kernels, and we define the Kobayashi rank as follows, this messy formula boils down to the following. If we are focusing on the finite ZP module, actually Kobayashi rank is the difference of these sizes. So how do we study this? Recall that we have this fundamental exact sequence. And there's a property of the Kobayashi ranks that allows us to obtain the following formula. So the sum of this Kobayashi rank is equal to the sum of the Kobayashi rank of this, which is the Pontryagin dual of of P infinity Selmer group and that. So if we are able to show that the Mordell wave rank is bounded, this bit is okay. The main difficulty is to find the Kobayashi rank of this bit, which is a byte that more than we can chew. So what we do is that we kind of interpret this Kobayashi rank in terms of objects where we can find the Kobayashi rank. This is the aim we are going to follow. So in Kobayashi case, he obtained the following results. So if we have a non-zero element in the Iwasawa algebra, and we can define the projective system by taking this quotient, and it turns out that if f does not vanish at this point, the Kobayashi rank can be given in terms of the order of f at this value, basically. Further, if we have a finitely generated torsion lambda module, hence we have the characteristic polynomial, and we can define the projective system again, then the Kobayashi rank of Mn is this, and also this can be explained in terms of the Iwasawa invariant. So this is this type of projective systems what he encountered, but in our case, we encountered certain Iwasawa modules, certain modules arising from 2x2 matrices. So we need to be able to calculate the Kobayashi rank of these kind of projective systems. So let me explain what I mean. So we have this matrix, and we define the lambda module generated by the columns of this matrix. And if we have two matrices, basically we define this in a similar manner. And we define this projective systems basically by taking this quotient. Here, omega is the polynomial that I mentioned in a few slides back here. And we say that A is special relative to an integer n if it satisfies the following. So if the cyclotomic polynomial divides the determinant for these numbers, then it divides either the first column entries or the second column entries. So under this restriction, we can find the Kobayashi ranks of this projective system, which is defined and is equal to the order of the determinant of A evaluated at this number. So that allows us to define certain auxiliary objects and split the Kobayashi rank of this x e to the chi n and allow us to calculate the number. So how do I do that? So I will just show you the matrix that shows up, and I will ignore the rest. So as I said, so the reason why we encounter such a thing is because of this object. In Kobayashi, so this is an inverse limit of some cohomology, we can ignore that. In Kobayashi's case, this becomes of rank 1, therefore it leads to some objects that I mentioned in his case. In our case, it is a lambda module of rank 2. And we define this compositum. This is the localization of K infinity at P. And we denote the coordinates like this. Also, let me introduce two more objects, sorry, which is a product of certain cyclotomic polynomials. Here, I take the evens and odd. Then this is the matrix that appears in our case. Also here, we can see the alternating bit. If you go back to the definition here, for the odds, one of them will vanish for the even part if I evaluate it at epsilon n, one of them vanish for odd numbers, the other will vanish for the even. So that also carries the information regarding the alternation. So this is what we found. We were able to split the Kobayashi rank of this into two bits. One part comes from the plus minus Selmer groups. This part comes from the projective system that we defined through this matrix. And we were able to prove that the Kobayashi rank of Xn is given by this formula. So let me remind you the statement again. So the Kobayashi rank is bounded independently of n. And if we assume the finiteness and define these things, the difference here regarding the size of the Tate-Shafarevich groups is given by this formula. And the idea was to use this fundamental exact sequence, obtain that using the Kobayashi property of Kobayashi rank, and calculate this bit here, which leads to the theorem, basically. So I will conclude with the final remarks. As I mentioned, we are working under the assumption that these plus minus Selmer groups are cotorsion. Under certain hypotheses, Brungel'in büyük bootcan'la prove that this is the case. So we are not assuming something crazy. And also in the beginning, I fixed elliptic curve and primes in a way that E has good supersingular reduction, but AP is 0. So the next target that we are going to focus on is to remove this assumption. And what we need to do for that is to study these local points, generalize them in a way that we can define Coleman maps and Selmer groups. So this is the main difficulty when we assume AP is not 0. Also, as I mentioned, Kobayashi studied modules, growth of modules of this form, but in our case, we encountered modules of this form. Of course, the natural question is that, can you find the Kobayashi rank of modules arising from D by D matrices? And this is going to be the other project that we are going to focus on. We are going to calculate the Kobayashi ranks of such modules, such objects, and that will lead to extend the case where Ley and Lim studied, basically, which allows us to study the elliptic curves over a broader class of number fields. So that is all that I have to say. So thank you very much for listening.
Thank you.
So I think I was a little bit faster, but I don't think nobody will complain about it.
Are there any questions?
So for non-abelian extensions of Q, say K is a number field, which is a non-abelian extension of Q. Do we have?
I can ask some questions.
Yeah, I guess one has a question.
I don't know who was speaking.
I can't hear anybody at the
I
moment.
think Jishnu was asking some question. Yeah.
Okay, you're saying something. Maybe you finish your sentence.
Yeah.
Can you hear me?
Well, I can hear everybody, so
Vishnu, maybe you can write in the chat.
Yeah, that might be better, I think. So I have second screen. I can see everybody. I can read the chat. So feel free to ask your questions in both ways.
So maybe I will ask a question.
Yeah.
So for non-abelian extensions, do we have results in this direction in Iwasawa theory?
In this direction regarding the Tate-Shafarevich group, or
So, for example, or in the Leopold conjecture and so on, because Brummer proved it for abelian extensions, right?
yeah.
Yeah.
So to be honest, I didn't check all the literature. I just put this result to convince that this is like there are some known cases. What I believe is under certain restrictions, I think there are known cases. To be honest, I haven't encountered any, but it is my fault. It is my lack of information. But I believe there should be some cases.
Oh, thank you. Yeah.
Not we should wait for the text or not?
Sorry, I want to ask you a question. Can you hear me?
Yeah, I can.
Okay. So I was wondering, do we have the p-adic function for the anticyclotomic tower? So is the
In certain cases, yes. For instance, if we restrict ourselves to complex elliptic curves with complex multiplication, we have Rubin's p-adic function.
okay?
So there are
But
some cases where we have p-adic functions, but in general, I don't think we have like in all cases.
okay, and so I would assume that in those cases of the CM complex multiplication, this results in the algebraic direction that you proved can be verified analytically.
Yes, that is true. Actually, in Sprung's article, well, he also had a separate article where he studied the similar behavior for the p-adic functions. So yeah, there are known cases where you can do the same for the p-adic functions.
Sorry, can you repeat the name of the author of the article?
Sprung, Florian Sprung. Maybe I can
Okay.
show you the last name here. Sorry, is here this author.
Okay.
He also studied the behavior of the p-adic functions like asymptotically.
Great, thanks. And one more question. Does the recent proof of the Stark conjectures imply any stronger form of the results that you present here?
A recent result of what?
A Stark conjecture.
Stark conjecture. So, well, if it leads to the Iwasawa-Mei conjecture, yes, it should be. But in order to prove the Iwasawa-Mei conjecture, you need to have like more than just Stark elements. But to be honest, I don't know if it would imply directly. I haven't looked at it in that direction.
Okay. And you mean Iwasawa conjecture over your imaginary number field, right?
Yes.
Right.
I think there is a question in the chat. Do we have the
Yeah, that
growth
was
of
the
Tate-Shafarevich group for the compositum of cyclotomic and anticyclotomic sublayers? Yes. Antonio Lei and I forgot his last name, but Poinsett, like 3 or 4 years ago, obtained certain formula for the, well, what we call is the maximum ZP extension over the ZP extension. Yes, this is the case. Sorry, I didn't give the entire literature because I was like focused on cyclotomic, anticyclotomic, so that was kind of my distinction. But yes, there is a case. There are some formulas over the maximum ZP extension.
No, I mean, so if you take the, so here you are only looking at the anticyclotomic sub-extensions again. But if you look at the compositum of the cyclotomic and the anticyclotomic, in the inert case, the Poncinet's article, it was that the growth, they analyzed the growth of model whale along some tau. But here I am asking the question that that if you have the, if you take the, so cyclotomic sub-extension you take at the nth layer and the anticyclotomic sub-extension you take. So you have the compositum, which is a Z mod p power n Z squared extension.
Yes.
Yeah, and so now the Florian Sprang and Lei have an article where they've analyzed the model whale growth, and they have shown that it's order of big O of p power n in this. Yeah. So, but I am asking about in the, do you know the growth of Tate-Shafarevich group for over this extension?
Well, I don't think we have any. I haven't encountered any at the moment because like the tools we are studying actually very new. Like these local points are very new. So in order to study that, you need to be able to define the plus minus Selmer groups, and these tools haven't evolved enough to study this compositum, I believe.
Okay, thank you. And another question is that so you know that Antonio has a paper where he studies the growth of signed Tate-Shafarevich group, the plus minus Tate-Shafarevich groups.
Well, which one you are mentioning? Because there are like 5
there is
probably.
a paper on MathZ where he has some theorems, and he does not study the growth, but he has some theorems on the signed Tate-Shafarevich group. So if you take the signed model whale group and then the signed Selmer group, you quotient it out and you get the signed Tate-Shafarevich group. It's a MathZ paper of and so did you, so the question is, in the inert case also you can take the signed model whale groups, and you can also define signed Tate-Shafarevich groups. But no one has yet, I guess, studied the growth of those in the inert case.
Well, Tate-Shafarevich group we studied, but we haven't studied in that direction. Yes, that is true. No one has done that.
Yeah, for example, here in the formula, in the asymptotic formula, you see that if the mu plus minus is 0 and lambda plus minus is, then still the growth of the Tate-Shafarevich group is not constant. I mean, it's not bounded. There's a lot of Qn here. It's always there. It's not bounded. But in case of signed Tate-Shafarevich group, this power Qn can vanish. I guess.
Maybe I
so.
can open the formula where we can follow easily.
Yeah, see this S 2 times Sn minus 1. This is always there. Even if the lambda minus and mu plus minus, these are all 0. Then even if these are 0, but the Tate-Shafarevich group always grows. But the interesting thing can be like if what can happen if you take the signed Tate-Shafarevich group, not the classical Tate-Shafarevich group. Then these powers can, I don't know what will happen, but
well, me neither.
Antonio has papers on signed Tate-Shafarevich groups. You can
yeah. But yeah, it is a strange observation. Yes. So is there a question? I start not being able to hear you.
No, thank you. I am done.
Okay. Yeah, thank you for the comment. Yes.
Okay, if there are no other questions, maybe we thank Erman.
Thank you.
Thank you, and we'll see you in 2 weeks.
Well, thank you, everyone. See you next time,
Thank
hopefully.
you. Bye bye.
Bye. Yeah.
Bye.
Thank you. Thank you.
Bye bye.